Hey kids, Charlie Busso here. We're going to do homework number 3. Correctly name the bond or bonds. Correctly name the bond or bonds. The formula for this is going to be NaF. I know that because sodium is a +1, fluorine's a -1. It's a 1-to-1 ratio. The name and the bond. So this is sodium fluoride. It's going to be an ionic bond. That's all you have to say. Ionic bonds are never single or double or triple. Methane, the formula, because you remember it, is CH4. Here we're going to have 4 separate single polar covalent bonds. 4 of them. This is a weird thing. Look at that, O3. That makes this ozone, kind of like where I'm from, Ozone Park. This is going to be what's called a resonating bond, and you just got to remember that one. It starts out with a double bond and kind of a fake bond on this side, and it's not going to be stable, so the fake bond jumps over here. So it goes from a double and a fake to a fake and a double, back and forth, and we get what's called a resonating bond. Silicon dioxide, beach sand, looks like this. Silicon's a non-metal, even though it conducts electricity. Silicon is going to be in the middle with 4 valence electrons, and oxygen is going to double bond on both sides, right? It's going to look like that. But if we look up the electronegativity values, silicon, element 14, has a 1.9, and oxygen has a 3.4. So we have 2 double polar covalent bonds. 2 double polar covalent bonds. NH3, you got to remember this one too, ammonia. Ammonia is going to look like this. I'm going to put them on top, the 3 bonds. Nitrogen has 5 valence electrons. Each hydrogen is going to come in on the top, left, and right. There's a difference in electronegativity. 2.2 is the electronegativity value for hydrogen, and 3.0. So here we have 3 single polar covalent bonds. The nitrogen bonds to hydrogen in a single polar covalent bond, then it bonds to another hydrogen single polar covalent bond, and then the third bond, they're all separate, 3 separate bonds, is another single polar covalent bond. Carbon dioxide looks like this. The oxygen is going to have a 3.4, and the carbon is a 2.6, so it's going to look like this. I'm going to draw these quick because they got to be in your head. We're going to have 2 double polar covalent bonds. This carbon makes a double bond to the left and to the right, and the oxygen makes a double bond, and the oxygen on the other side makes a double bond. So we have 2 separate double polar covalent bonds. Sodium hydroxide, sodium is a metal, makes a +1 ion, and hydroxide is a -1, so it's going to be NaOH. Now, the sodium to hydroxide bond is ionic. Plus, now this is tricky business, inside of the OH, that bond right there is going to be a single polar covalent bond. So this has both ionic and polar covalent. So you have to be careful on something like that. Aluminum fluoride is AlF3. We're going to have 3 ionic bonds. Aluminum to fluorine again, and aluminum to fluorine again. This is called lithium bromide, and it's going to be ionic. There's only 1 lithium and only 1 bromine. Iron Roman numeral 2 sulfide. That means it's going to be FeS in a 1-to-1 ratio. This is also ionic. Now, this is important. These share 1 pair of electrons. No, these transfer 1 electron. This transfers 2 electrons, but it's not a double. There's no such thing as double ionic or triple ionic or even single ionic. It's ionic. This transfers 1 electron, this transfers 2 electrons, but they are not sharing, okay? Carbon tetraiodide, carbon with 4 iodides. Now the carbon is a 2.6 electronegativity, and you have to look up iodine because you never want to just guess, and iodine has a 2.7. Now these numbers are really, really, really close, but in high school chem, if it's not a difference of 0, then it's slight, this is very slightly polar. We're going to have 4 single polar covalent bonds. Now, I have to say, some teachers might say that these are so close that it's irrelevantly polar. I would argue with that. It's either polar or it's nonpolar. And this is just a little bit on the polar side. Now, with C2H2, the way this bonds together is going to look like this. So we're going to have on this side right here, and also right here, there's going to be 2 single polar covalent bonds between carbon and hydrogen on the left and carbon hydrogen on the right. And in the middle, we're going to have 1 triple nonpolar covalent bond for the 2 carbons. Now, carbon monoxide is one of the trickiest ones we're going to have all year. The carbon starts out with 4 dots, and we're going to try to make a double bond like that. We're going to try to do this, but look what happens. The oxygen gets 8 electrons and has the octet, but the carbon only has 6. So this doesn't work that way. What really has to happen, I'm going to draw an arrow. What really happens is something weird works out. The carbon, which has 4 dots, does make a double bond to the oxygen, but the 2 electrons that were on the top move into the middle, and we end up with something that I show this way. It's a double bond plus something weird called a coordinate covalent bond. So we have a double polar covalent plus the coordinate covalent bond, and that's our only example in high school chemistry of a coordinate covalent bond. And in this case, how you can think of it is the oxygen and the carbon do exist in a CO molecule, but the only way for it to bond is to break the octet rule, and to do that, oxygen coordinates it so that carbon can feel like it has the octet by sharing an extra 2 electrons of its own, but it's not a triple bond. A triple bond involves sharing 3 pairs of electrons. These 2 atoms share 2 pairs of electrons, and oxygen then lends another pair in the middle. So it's kind of like a 2 plus a funky thing, and that funky thing is called a coordinate covalent bond.